let's begin. So this was the example that we had on the board last time. Now we're going to actually do it. So you're not going to be asked to use all three of these methods in one problem. I'm just going to do three of them so you can see how it will work. But usually one problem would be, so for example on an exam or a final, one problem would just say, oh, approximate the error under this curve on this interval using right-hand endpoints, or left-hand endpoints, or midpoints. They'll usually ask for one of these. Another way that you can see this phrased, instead of using three subintervals, they might say three rectangles. Or they might say using n equals 3, and they'll expect you to know what that means. So, but otherwise, the question is going to look pretty much like this one, the problem. So, approximate the error under some curve on this interval using three subintervals, or three rectangles, or using n equals 3, and one of these methods. So, last time I described these in pictures, so let's see what the calculations will look like. So, I'm doing the right-hand, so remember we call that R sub n. So here's how I like to do it. I like to actually draw in the interval. Just have a visual frame of reference here. And obviously this is from 0 to 6. And I want to use three subintervals, so I'm going to dissect this into three pieces. And I will immediately then compute my delta x, which you might recall is b minus a over n. The b is the 6, the a is the 0, over n, which is 3 in this case. So this means my delta x is 2. And what that tells me is that the jump from each one to get to the next one is going to be 2. So that's going to be 2, then 4, right? Because I keep adding 2. And you'll see in the last situation, I end up with 6, right? So that's my delta x, and that allows me to actually fill in this interval. Now I just want to know which one of these x values are important for me. And that all comes down to which rule am I thinking of. So the right-hand rule is going to tell me choose the points on the right side. So for every subinterval, I am going to choose the point on the right. So in the 0 to 2 subinterval, 2 is on the right. In the 2 to 4 subinterval, 4 is on the right. In the 4 to 6 subinterval, 6 is on the right. I'm just going to go through and pick all the numbers on the right side of the subinterval. And those are going to be the points of interest. So my R sub 3 is just going to be, you don't have to write this, but just to kind of jog your memory, because we're going to be talking about this soon. This is the summation. Technically it would be k goes from 1 up to 3, right? Because this would be, here, remember the notation, this was x0, this was x1, this was x2, this would be x3, of f of x sub k. So I'm going to want to take x1, 2, 3. This sigma says I'm going to plug in 1, 2, and 3, whatever these values are, and then add them all up, times r delta x. Now, this delta x, you can think of it as being a part of this term, and you're just adding up things of this form. But we also know that we can factor constants outside of our summation. So I can also just think of it as adding a bunch of f's and then multiplying by that number. Either way, what you would actually write down at this point is it's going to be f of 2 plus f of 4 plus f of 6, all of that times delta x. What does that mean? Well, you actually just go to your function and you plug that number in. That's going to give you the height. So this is going to be 6 times 2 minus 2 squared plus 6 times 4 minus 4 squared plus 6 times 6 minus 6 squared. all that times our delta x, which in this case is 2. Of course, that's going to be 0. And this is going to be 12 minus 4 plus 24 minus 16 times 2. And what's that? So this here, that's minus 20. That gives us a plus 4 plus the 12. That's 16 times 2, 32, right? That's our approximation for the area. I would assume that the area here, which by the way I didn't actually draw it, it's not really important. The area we're concerned with is actually going to look like that, where there's a 6 here and a 0 here. We care about this area. Now, that's not exactly what the area is, but that's my approximation for the area. If I actually split this into 3 sections and then erect rectangles based on the right side, this will actually give me 0. So I'm actually using these 3 rectangles. This here, that rectangle would have a height of 0 because the right side, which actually makes sense. You see that here, this gave me 0. So the area of these 2 rectangles, my approximation for the area under the curve is 32. This is the right-hand approximation. So that's how it would actually look for you to actually write out one of these problems and actually build it up based on what this notation actually means. So that's it. That's all it is. B. If we wanted to use the left-hand approximation, again, I'll go through the same process. I'll just write this down. Now I want 3 equal parts. I would find my delta x. This is b minus a over n. This is 6 minus 0 over 3. It's going to be 2. So I'm just going to start here and keep adding the delta x. That's going to be 2, 4. Then I know I want the left-hand endpoints. So on this interval, pick the guy on the left. On this interval, pick the guy on the left. On this interval, pick the guy on the left. And so L sub 3 is going to be f of 0 plus f of 2 plus f of 4. All of that times delta x. And now I plug them in. 6 times 0 minus 0 squared plus 6 times 2 minus 2 squared plus 6 times 4 minus 4 squared times 2. So that's going to be 12 minus 4 plus 24 minus 16. So again, this is positive 4 plus 12. That's 16. So we get actually the same approximation. So last time, based on the picture we drew, I told you that, oh, the right side would give you an overestimation. That was because the curve was just always going up. The left side would have given you an underestimation because the curve was always going up. In this particular case, for this particular case, based on how our function looks, it just turns out that the right and the left side happen to give you the same answer. So they don't always have to disagree. So you would get the same approximation either way here. Now the midpoint, and that would be the answer to this part. Every now and then, sometimes they ask a question like that, where they would follow up to this. If there's a second part to a problem like this, it would be something like, is the approximation an overestimate or an underestimate? They'll kind of ask you to judge how your answer compares to the real answer. And a lot of times you can tell that just from the picture. You can say, well, since the picture is increasing, the right hand approximation is always going to give me something bigger, and the left hand is always going to give me something smaller. Another thing that they could do is they can ask you to do one of these, find the exact area, either using a similar method or some other method, and then talk about is your approximation an overestimate or underestimate, and then that would be obvious. You just compare the 2 answers, right? So those would be the follow-ups. You wouldn't be asked to do several of these at once, but they could follow up with a few other questions, conceptual ones. So that's the left hand and the right hand approximation. Now the midpoint approximation is the same in spirit as these. It just takes a little longer to actually set this guy up. You guys had this question copied down last time, so get rid of that. So for C, I'm using the midpoint approximation. I would start the same way. Let's make this a little longer. 0 to 6. I would split it in 3. I would compute my delta x. It's going to be b minus a over n, 6 minus 0 over 3, which is 2. So I'm going to start here. I'm going to add 2. Now, for the midpoint approximation, remember what we want. We actually don't want any of those numbers. We actually want the number directly in the middle. So now you might wonder, well, what is that? Well, here's how you would start. Here, it should be obvious what the answer is, but for some reason, let's say these numbers were like fractions and it wasn't completely obvious to you what the answer is supposed to be. What you would do is you want to find a number that's directly in the middle of these two numbers. Arithmetically, that's what? That's the average, that's the mean average. So for your x1 star, you would just average the first two. It's pretty much going to be like x2 plus x1 plus x2 all over 2. In other words, that's going to be 2 plus 0 over 2, and I'm using 1, and that would be the first number you fill in. 1. And once you find the first one, you don't have to average to find all the other ones. You just, from that point, keep adding the delta x. There will still be delta x apart. So from the 1, I'm going to add 2, which gives me 3. From the 3, add 2. That gives me 5. And these are the numbers that I use. Right? So for the midpoint rule, you don't use any of the numbers that actually show up in the first place. You want the numbers in between them, exactly in the middle. Average the first two to get the first starting point, and then you keep adding the delta x to get all the others. There are still going to be delta x apart. And other than that, you continue the same way now. So n sub 3, this is going to be f of 1 plus f of 3 plus f of 5 times delta x. And you're going to just plug this into the function. 6 times 1 minus 1 squared plus 6 times 3 minus 3 squared plus 6 times 5 minus 5 squared times 2. That is 6 minus 1 plus 6 is 18 minus 9 plus 30 minus 25 times 2. And so this is minus 10 and minus 25, that's minus 35. With the 30, that gives me a minus 5. With this, that gives me 13, and 6 gives me 19. And then 19 times 2 is 8. So this one gave me a bigger answer. So that kind of makes sense. None of the rectangles gave me a 0 area. So yeah, the midpoint one is actually the biggest one here. As for who is closest to the actual answer, at this point, we don't know. But that's any questions on this? So that's how you would approximate an area using a finite number of rectangles. It depends on the method that you're asked. You have the right-hand rule. On your interval, you pick all the numbers on the right. If you have the left-hand rule, pick all the numbers on the left. Midpoint rule, pick all the numbers in between them. Find the first one by averaging and adding the delta x to find all the others. Then you're going to evaluate the function at all of these numbers, add them up, and multiply by delta x. essentially, if you recall, this is the height times the width, height times the width, height times the width of each rectangle. That's how you would approximate area using a finite number of rectangles. So at this point, before we move on to the case that we really care about, how do we find the exact area? It's important at this point, well, I should have told you before, but it's important at this point to actually tell you what this is called, because remember, it's not only important to know what you're doing, you have to sound like you know what you're doing. So the above is how we approximate area using a finite sum of rectangular areas. These sums, I'm talking about the guys that look like this, f of x I times delta, f of x k. Your textbook uses k, I'm used to using I. If these sums that look like that are called Riemann sums. It's named after a person's name. So the way we do calculus now, in Calc 1, 2, and 3, and pretty much anywhere you go, the way we do calculus, the notation we use, kind of the way we think about it. Well, a lot of it, yes, due to Newton and Leibniz, but just how we actually formulate it and write it down on paper, a lot of it is due to this guy. He's a mathematician named Riemann, who actually described this process of integration in his PhD thesis. And he described a bunch of other important theories. So the way we actually do this is due to a mathematician named Riemann, which talked about this about 100 years ago. So this is how he developed the integral. So the idea of this sum, there are many ways you could actually do it, as I've been saying. There's no reason why we had to have equal subintervals and any of that. It's just that's how he decided to set it up. He wanted to prove certain theorems, and so he just reimagined everything that we knew before, and this is how he thought of finding areas. You know what, let's just use an equal amount of distance. We call this a subinterval, we'll call it delta x and blah, 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 right? And he developed this. So we name it after him. This is called the Riemann sum. The above, you refer to. As finite Riemann sums. Why? Because we use a finite number of rectangles. Okay, so now let's go to the question of interest. How would we find the exact area under some x? You just know how to approximate it. What would it mean to find the exact area? So here's something you would notice. Note. With these approximations, you're going to notice something after you've constructed a few of them, and you can just look at the picture and it will actually be obvious. The more rectangles, the better, right? The better the approximation. you can realize that, okay, if I had some curve I wanted to approximate the area under between A and B, well, let's say I use two rectangles. Okay, you would miss all of this, right? So you say, okay, let's use more. Let's up it a little. Between here and here, let's use 6 rectangles. And then you can do this, 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 this. And you'll notice that you actually miss less. You get more pockets, but all the pockets are smaller. And you can, right? So this is man, and this is, okay, it's I. Right? But you know what would be good? What would be the best number of rectangles to use? What do you think? 42. No, that's just a... The best thing to do is to actually use an infinite number of rectangles. Which, of course, you can never actually do, but we're math people. We don't care about what you can actually do in reality. We care about what you can do in theory. Pretty much, just keep putting in rectangles. And if you're like, okay, we're missing too much space, put in another rectangle. Okay, put in another one. Okay, still too much space. Put in another rectangle. We have more to spare. Put in, right, you have an infinite amount of rectangles. So basically you can kind of just start filling up this space with all the rectangles you want. And if there's more space, just fill it in with more rectangles. And in theory, what's going to happen is all the little spaces, even until they get smaller than you can even see, all of the little spaces are going to be filled in. And so that's the best. Right? That's how you kind of do it. So you miss gaps whenever you use a finite number of rectangles. So here, let n go off to infinity. Right? Now we can't actually plug in infinity into a formula. It's not a real number, which is why, once again, the limit saves us. So this is how we are going to actually find the actual area. We will theoretically use an infinite number of rectangles. So use what's called an infinite Riemann sum. Just use an infinite number of rectangles in your Riemann sum. So this is basically the area is going to be equal to, again, it's f of xk times delta x. But now you let your k go from 1 or 0 or whatever to infinity and beyond. Right? And that's how the idea of the infinite sum comes into play here. And we actually know what that is. We actually know how to compute this. Recall. When we write the sum from, it's not actually going to matter where we actually start. We're using an infinite number. That is actually equal to the limit as n approaches infinity of. Just, you find the sum of the first n terms, and then you just keep making n bigger and bigger and bigger. So we just find the Riemann sum in terms of n, and then we take a limit as n goes off to infinity. If this adds up to a number, we can find, we call that number the area under the curve. And unders in quotations, I'll talk about that a little bit later. So this is also something that you might be asked to do. Computing areas based on first principles. This is kind of right up there with like computing derivatives using the limit definition. It's how we developed it, it's what the definition is going to be. This is how we can define the area under a curve. We can say the area under the curve is that. Just look at an example. So you can see how you'd actually put this into play. So find the exact area under. We're going to change the function here, but it's not a crazy function, x squared, on, say, 0, 1, using. So they might say something like using the limit of a Riemann sum, or using infinite Riemann sum, or something like that. But once they ask you for the exact area, they didn't ask you to approximate the area. You know you want something like this. If you have to do it using a Riemann sum. So here I have my y equals x squared doing its thing. Here's 0. There's 1. I want to know what is this area here. Not an approximation of the area. What is the exact area under that curve? So here is how it is going to be set up. Me drawing the interval and drawing in how many sections I'm going to have doesn't even actually make sense in this case. But I still want to know what my delta x is going to be. This is going to be b minus a over n, where n is the number of rectangles I'm going to use. Now, I can't actually plug in the number of rectangles, so I'm going to just leave it as n. So this is 1 minus 0 over n, or just 1 over n. What's that? So now, what I can do is, we know that our a equals 0 and our b equals 1. I want to know what do the xk's look like. And last time I gave you an equation that gave you the xk's. It's a plus k times delta x. So that's going to be 0 plus k times 1 over n. Otherwise, this is k over n. This means my f of xk is just f of k over n, which is, my f is x squared, so that's just k over n squared. That means, so I just go through, take my time, I'm finding all the pieces in the formula. The area is going to be equal to the limit as n approaches infinity of. And it actually doesn't matter at my starting point. I'm going to get an infinite number of rectangles. Of that times f of xk delta x. And that will be equal to this k over n squared times 1 over n. If I can compute that limit, that is going to be my area according to the infinite Riemann sum. Now, that might look familiar to you if you've been paying attention. We actually did that example. Actually, that specific example. This is where it came from. So you might remember that the answer was a third. But let's just run through it again. It is something that you will need to know how to do. So we would realize that here the summation actually thinks of k as the variable, which means the n's are constants, which means I can factor them out. I could factor out an n cubed, and I'd be left over with the k squared here. Now I have this guy, which we all memorized the formula for by now. I told you guys you have to memorize that. What does that become? N? N plus 1.
Something over 6.
Plus something over 6. You can't write that. Okay, it's that. N times n plus 1 times 2n plus 1, all over 6. Now, notice that we're taking the infinite limit of a ratio of polynomials, which we have a shortcut for that. I don't care about any of these guys except the biggest one. This is going to be 2n cubed plus a bunch of stuff that I don't care about. And in the denominator, I have 6n cubed. So because the highest power is the same on the top and the bottom, we take the ratio of the coefficients. That's 2 over 6, or 1/3. So the area under this graph is actually a third. And the units depend on whatever units you're measuring your axes in, of course. So if you're measuring your axes in inches, this area is going to be 1/3 squared inches. That's an example of how you find the exact area. Now, that's finding the area by an infinite Riemann sum. Go through the same motions. You don't need to draw an interval because it's not going to matter anyway. Figure out what your delta x is. It's always b minus a over n. So it's always going to be some number over n. Figure out what you would have known what your b and a are here. So now you can find the xk. It's always going to be a plus k delta x. You're always going to start at the left and add the delta x's to create all the other guys. So you'll get an expression over here that's going to have k's and n's in it. Then you have to find the function evaluated at that point. So you're going to take this as the x value and plug it in everywhere you see an x in your function. In this case, we have that. And then this is the definition, which by this time you would have memorized. You simply plug these in to that definition. You will get a summation where you're now just going to compute the summation based on the principles that we did last time. Anything that's not a k, you can factor it outside, and whatever's left over, you can use the formula for that. If there are several terms, like was something plus something, know that you can take the sum of each thing individually, and then you do this in each term. Factor out anything that's not a k, so that you isolate something that you would have a formula memorized for, and then you put in the formula. Take the limits, which by now you should be an expert at limits, and that answer is going to give you the area under the curve. Now, it is of course possible for the limit that you end up here to not exist, and that just means we cannot find the area under the curve by this method, but it's Calc 1. If I ask you this, it will exist. There will be a way to find the area under the curve. Okay, that's that. But here's something that you would note. Observation. This process can get very annoying, very fast. Let me show you an example. Suppose I want the area under f of x equals 2x cubed minus 3x squared plus x plus 1, right? Which in and of itself isn't a crazy function. That's a polynomial. Polynomials are nice. Polynomials are our friends, right? Polynomials, they're continuous everywhere. You know, we can find derivatives easy, you know, and all that stuff. So these are, it's a really nice function all told. However, try to do this with that function. If someone said, let's make all these positives, on, let's say 1 to 4. What would you actually have to go through to figure that out? Well, if we were to go through this process, here's how that is going to look. Well, you would start with your delta x. It's going to be b minus a over n. This is going to be 4 minus 1 over n. This is 3 over n. Then you'd want to figure out your xk. Your xk is going to be a plus k delta x. This is going to be 1 plus 3k over n. Then you have to find your f of xk, which is going to be, well, you're going to take this, plug into every x here. That's going to be 2 times 1 plus 3k over n cubed plus 3 times 1 plus 3k over n squared plus 1 plus 3k over n plus 1. And then you're going to, okay, say the area is going to be the limit as n approaches infinity of the sum, k goes from 1 up to n, of that whole thing times your delta x. And then, at this point, you'd be like, nah, not doing that, right? Because what would you actually have to do here, right? You'd have to cube this guy, right? Which is going to give you like 4 terms, right? You know that a plus b all cubed is a cubed plus 3a squared b plus 3ab squared plus b cubed. So you're going to have to do that. Then you're going to have to square this, you know, a plus b all squared is a squared plus 2ab plus b squared. Then you just said this and that. You're going to have to group the like terms, so group all your k cubes, group all your k squares, group all your k's, group all your constants, multiply through by 3 to the n. Then you're going to take the sum, apply to each of those things, factor out everything that's not a k, and then apply the formula on all of those things. And this is a very nice function. If I were to, just with a flick of a pen, if I change this 3 to a 4, now as far as a Calc 1 student is concerned, that's impossible. Like, can't do it. Like, I don't know how to add up the first n fourth powers. Hey, if I put that a half, what is the sum of the first n square roots? Right? Like, it gets really hard, really complicated. It gets really, really annoying really fast, right? At some point, it's just like, I can't keep doing this. I can't do this anymore. You know? I don't get paid enough for this, right? At this point, you realize that you're no better than that guy slicing things into rectangles and counting them, right? It's just going to be a very labor-intensive process. And the guy counting the rectangles, yeah, that guy, he's better than you at this point because he's going to get to an answer faster than you if you had to do this by this method, right? So yes, it's sophisticated. Yes, we can use all this fancy notation. We can feel like we're, you know, king of the world. But when it comes down to the practicality of the situation, not very practical. So that isn't good enough. So the question is there a better way to actually get this thing done? And the answer, surprisingly, is no, there isn't. I guess that's the end of the story. I'm kidding. No, of course there is. Of course there is. What do you think people do in Calc 2? Guess you have to go count rectangles. That's what the Calc 2 kids are doing. They're just sitting around counting rectangles. No, that's not what they're doing, because this is not the end of the story. There is a better way to do this. So, now, I'm not going to do that. We're going to do things a better way. And we've seen something before. Something quite useful. Remember that distance velocity graph thing? That same example where we're traveling 150 miles over 3 hours, and then we drew the graph of the distance function, and then we drew the graph of the velocity function, and we kind of noticed that if we looked at the area under the velocity on some interval AB, in our example it was 0, 3, this was actually equal to the position function evaluated at B minus the position function evaluated at A. We also understood the relationship between these two functions. In fact, the S was the antiderivative of the V. And so we might think, does something like this work in general? Like, I mean, even if we weren't talking about distance and velocity, and I couldn't actually see this on the picture, and the functions weren't that nice, could something like this actually work out? And it turns out the answer is yes. Something like this works out in general. This idea is true in general. It's referred to as, there's something called the Evaluation Theorem. AKA, sometimes called the Newton-Leibniz formula, as a nod to our forefathers. So there's something called the Evaluation Theorem. Pretty much tells us how to evaluate areas using this shortcut. And here is what it says. Let f of x be continuous on AB, and big f of x is an antiderivative. Then the area under F on AB is going to be the big F of B minus the big F of A. And under here should be quotations. Again, I'm going to actually talk about why the under should be quotations. But something like this is true in general. We can find the area under a curve by just looking at its antiderivative. It's called the evaluation theorem. I can find the area just by evaluating the antiderivative at the endpoints. Why is that true? So let's start with the f of b minus the f of a. What is that going to be equal to? Well, notice that this is f of, let's just rename things very suggestively. Our b was xn and our a was x0. We used that notation last time when we were slicing things up. And here's what we're going to do. We are going to add and subtract a bunch of terms, convenient terms. So what I'm going to do is I'm going to subtract f of xn minus 1 and add f of xn minus 1. I'm going to subtract f of xn minus 2 and add f of xn minus 2. Dot, dot, dot. And I keep going. Eventually I get dot, 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 dot. I will eventually end up with something like f of, let's say I'm 2 steps away from the final, f of x2. That's the end point of something. I'm going to be subtracting f of x2 and adding f of x2. I'm going to be subtracting f of x1 and adding f of x1. And then finally I would have the f of x2. Okay. So I added all these terms in the middle. And now I'm going to think of them in certain pairs. So consider that pair, and that pair, and there's that pair, and there's going to be that pair, and this pair, and this pair. So notice I have f evaluated at one point on a subinterval minus big F evaluated at the other point of that subinterval. This is f evaluated on the right point, f evaluated at the left. Similarly, f evaluated on the right, f evaluated on the left, f evaluated on the right, f evaluated on the left, blah, blah, blah. And you might say, where have I seen something like this before? And we have seen something like this before, and I'm sure you all remember where it's from. And you're going to be like, well, it's obvious, Jhevon. We saw something like this in the mean value theorem. So recall, just a side note. Forever and a day ago, we learned about something called the mean value theorem. So the mean value theorem says if f is continuous on AB, differentiable on AB, then there is some C in AB such that f prime of C is equal to, well, f of B minus f of A over B minus A. And notice that we could have thought of that as f of B minus f of A is actually equal to f prime of C times B minus A, right? Now, B minus A was just the distance in the two x values. I could actually think of that as a delta x. So according to the mean value theorem, if I'm looking at a continuous function on some interval, if I evaluate the function on the right point and evaluate the function at the left point and subtract these, and the function is continuous and differentiable on the interval, then there is going to be some point in the interval where the derivative at that point times delta x will give me that difference. Now if you look at that difference, and look at all of these differences, you'll notice that I can actually apply this equation over and over and over again. And you might say, well, how do I know that it fulfills all these functions? Well, f is an antiderivative, meaning I can differentiate him to get someone else. If you're differentiable, you're automatically continuous. Remember, we know that the derivative does not exist where you're not continuous. So the mere fact that big F prime exists, in fact, I know who he is, he's little f. The mere fact that that exists means he's continuous and he's differentiable automatically, just by assumption. He has both of those properties, which means the mean value theorem applies to big F on this interval, which means I can replace each of these pairs with expressions that look like this. So it turns out, by the mean value theorem, I can replace this by there is some big F prime at some point, let's call it C1 in this interval, such that if I take the derivative of that times delta x, it will actually give me that. Plus, I can keep going. There is some other point in this interval where if I take the derivative of that, call that point C2, times delta x, it's going to give me that difference. This has to exist. There will be some other point in this interval, and I think you can actually see the idea of what I'm going to do. I can follow that all the way down to the end. At this point, that means that there is going to be, at this point I would have gone through n of these things. So there's some point Cn that's in this interval, such that if I take the derivative of the function times delta x on that interval, it will give me that difference. I know this exists by the mean value theorem. So now I look at each of these pairs. But what is big F prime? It's little f, because big F was the antiderivative of it was right here. So this means little f of C1 times delta x plus little f of C2 times delta x plus little f Cn times delta x. What does that remind you of? That reminds us of a Riemann sum. That is just another way of writing f of ck times delta x. K goes from 1 up to n. That's exactly what that is. That's a Riemann sum. Yes. Riemann sum. So it turns out that this difference is actually equal to a Riemann sum. But that's not the exact area. In order to find the exact area, we need a limit. So I'm going to take the limit as n approaches infinity on both sides. Now, this guy doesn't have any n's in it, so the limit as n approaches infinity of that is just the same thing. And it turns out that this is just going to be the limit as n approaches infinity of k equals 1 up to n of f of ck delta k delta x, which is equal to the area under f. That's awesome. Because you see now, that gives me a nice little shortcut. And now I'm going to introduce notation, which by doing this, you are going to see that the notation makes a lot of sense. So this is called the evaluation theorem. It's a very, very important theorem. I'll show you just how important it is in a little bit. So this is called the evaluation theorem. Turns out this difference is actually a Riemann sum. We can construct it, and based on the assumptions of our function, we have to have this by the mean value theorem, which means we get a Riemann sum. And so I can compute this Riemann sum. This messy thing over here that I showed you an example of how messy it can get. I can actually, instead of doing that, why not do this? Find the antiderivative, plug in the values. And the nice thing about it is, especially for the thing that I showed you before, we actually know how to find the antiderivative. We have a bunch of rules. In fact, all our derivative rules come to help us here. They come to our aid. And so we can actually use the derivative rules, flip them around, and compute what this number is supposed to be. Then just plug in the endpoints into that number, into that function, whatever it is. This is monumental. It calls for a new notation. Leibniz, he's the one who came up with it, and we continue to use it this day. Because Newton's notation for this wasn't too pleasant. So it turns out that we will call this sum the infinite Riemann sum. K goes from 1 to infinity of f of xk times delta x. It is now forever and always denoted as that elongated s, where we put the a and the b on the s. That shows, so this is on AB. That shows the interval that we're considering. And then we write f of x dx. And of course you realize, hey, that looks very familiar to the notation that we had for antiderivatives. And yeah, because it is an antiderivative. So this guy, and this is called the definite integral. So remember the antiderivative, just if we were finding it in general, the plus c case, we call that the indefinite integral. This one's called the definite integral, because you're not going to have any plus c's. You're going to actually plug in numbers and you're going to evaluate the function. And if there was a plus c here, then he'll subtract the plus c from that part. So there's going to be no plus c. So we're going to get an actual answer here. So we call it the definite integral of f of x from a to b. So you say from the bottom to the top. Sometimes I hear students say from this to that. No, you say from this to that. Okay. So that's called the definite integral of f of x from b. In this notation, again, you have to sound like you know what you're talking about, so let me actually just explain to you what the individual pieces are. This s is called the integral sign. The a and b are called limits. A is the lower limit of the integral. B is the upper limit of the integral. The function f in this situation is called the integrand. And this is your differential. And again, there's an area of math that really goes into depth on the theory behind this guy, but the only thing you need to know is identifies the independent variable. So it just says the axis that I'm slicing up is the x-axis. Right? There is a formulation where you can slice up the y-axis instead, and so you use f of y dy. And when you go to Calc 3, you're going to realize that we can actually slice up any curve we want, and that's going to be called a different kind of integral. But this is just your regular run-of-the-mill Calc 1 single variable definite integral. And it is the area under f. And by definition, which I just erased, it is actually the value of an infinite Riemann sum. But because of the evaluation theorem, we actually have a shortcut for computing it. So, the evaluation theorem. F continuous on AB, big F, an antiderivative. Then it turns out that integral from a to b of f of x dx is going to be big F of b minus big F of a. That's called the evaluation theorem. So I'm just rewriting it with the nicer notation. Here's another interesting fact. suppose I look at one of these Riemann Sum guys, and I look at it as if it were some function. So suppose I have big f of x equals something that looks like this. The integral of a little function with respect to some other variable, let's call it t. And I'm integrating from a constant up to x. So remember, this is just some infinite Riemann sum on some interval c to x. This is like that function that I spoke about last time, the a of x, where it's finding the error from some fixed point, and you're just extending it, and it's finding the error under the curve as you move along. So let's say I can write that as a function, which I call big F in this case. Now, for various reasons, we might ask the question, what is the derivative of such a function? So if I have a function that's defined as an integral, if I were to differentiate such a function, what would the answer look like? Here's how we're going to figure it out. Let g of x be any antiderivative of f. So I am going to assume this thing is something that can actually be computed, meaning the integral of f of x is something that makes sense. So there is some antiderivative for this guy. Let's call him big G. Then, by the evaluation theorem, my big F is going to be equal to, the evaluation theorem says this guy is equal to his antiderivative evaluated here minus the antiderivative evaluated here, which means this is going to be the antiderivative evaluated at x minus the antiderivative evaluated at c. That, of course, means now I can start taking derivatives. F prime of x is going to be the derivative of that. Well, that's g prime of x. And g of c, well, that's a constant. So the derivative of that is 0. So it turns out that f prime is g prime. But what is g prime? Well, g is an antiderivative of f, which means g prime is f. So it turns out the derivative of the big F is f of x, little f. In other words, here's what I'm trying to tell you. If you were to differentiate an integral, the only thing that's going to happen, the derivative is going to cancel the integral. This guy's going to kill that guy. And you're just going to have the original function. Which kind of makes sense based on our definitions. The derivative reverses an integral. An integral almost reverses a derivative. It doesn't quite reverse it because there's all this plus c that you're not sure what it is unless you're given more information. So you can think of the derivative and the integral as almost inverse operations. One will undo the other. The integral, though, it does it in an indefinite way, but the derivative can undo an integral exactly. Now, these two facts are very important. Muy importante. Is that how you spell that? If it's spelled incorrectly, that's good. Because I want it to stick out in your mind that these two statements that I just made, the evaluation theorem and this particular statement, they're very important. Together, we call them the title of the next section, 5.5. So you take the evaluation theorem, which is a very important fact that we know that helps us to compute these infinite Riemann sums in a very convenient way, and take the fact that if I differentiate an integral, it just gives me the original function back. Putting those together gives us the fundamental theorem of calculus. So it might seem strange, oh, we just proved this in like half of Calc 1 class. How fundamental could this possibly be, right? It's actually really fundamental. It's why you're all here, right? This is the theorem that connects two branches of math that were, for centuries, thought of as two separate things. You had the people over here figuring out areas, you had the people over here figuring out rates of change. It turns out they were both working at the same problem from both different sides of the wall. And so this theorem says let f be continuous on an interval a, b, and big F of x be an antiderivative. I'm giving it a lot of board space because it's actually really important. Then we know two things. One, called part one. The area under f on the interval AB. The integral of f from a to b is equal to big F evaluated at B minus big F evaluated at A. And part two of this theorem says that if I were to differentiate an integral, I just get the original function. This is called the fundamental theorem of calculus. It tells us I can figure out areas by reversing a derivative. So if I know how to find an area and I know how to find a derivative, they actually play nicely together. Moreover, one reverses the other. The derivative will reverse the operation of the integral in turn. This is fundamental. It really stitched together two separate areas of math. And it was the beginning. It's the beginning of, now let's make a class out of this and force kids to learn it all over the country. This is so important. Everyone needs to know this. We need to tell everyone, right? And so that's calculus. It's based on this theorem. The fact that we can study it in the way we do, the fact that we can figure out one thing by doing another thing. When we're talking about derivatives, we can use an integral to talk about derivatives. And if we're talking about integrals, we can use a derivative to talk about the integral. We can play off of each other and figure things out. It's a very fundamental idea. And in principle, it's a very fundamental thing. Because things like that happen all the time. I tell you guys about like Fermat's last theorem, the proof that took like 350 years to prove. But Andrew Wells proved it in 94. Yeah, pretty much what he had to do was use a completely different area of math than what everyone, because this kind of question, like in Fermat's last theorem, was considered, number theory. People are just figuring out what integers divide into what other integers and things like that. To figure out the proof, he went to a different area of math called elliptical curves, where he had a bunch of mathematicians sitting around studying a certain kind of function, a certain kind of curve, with a very specific formula. It's like y cubed minus 5x squared or something like that. And they were studying all the functions that look like that. And he went there, and he figured something out that allowed him to come back and do that one, right? So this, in principle, is a very important idea. Everything's connected in some way or another. And so that's why now you have some areas of math called category theory, where people pretty much go around in different fields of math and try to find the connections between them. Because if they can find a very important connection, they can figure out a lot of things. So there's a huge part of math research which its job is to kind of do the kind of thing that the fundamental theorem of calculus does. Connect different branches of math. What is the connection? What is the things that are similar? Can we use the problems we know how to solve over here to figure out problems that we don't know how to solve over there? Very important theorem, not only for calculus, but in principle it's a very important thing for just figuring out different bodies of knowledge in general, important to life, right? You don't want to always think of everything as compartmentalized. A lot of people do that. But everything bleeds over into your life, right? You know, so there's like always those people who believe that, you know, math class was a waste of time, I've never used this thing in my life, and they just don't realize that math is everywhere in your life. Like everything bleeds into it. Every time you think there's a body of knowledge that it doesn't really matter for me, you use it in your life at some point. I was teaching my finite math class about matrix multiplication and stuff, and they didn't really like it. They were complaining. Then I taught them about Markov chains. Why do I have to do this? They're complaining. I'm like, are we ever going to use this in our life? And I'm like, dude, you use this every day, multiple times a day. How do you think Google works, right? It works on matrices and Markov chains. Like what I just showed you built $1 billion company, okay? So while some people were there, oh, I'm never going to use this in my life, right? Larry Page and Sergey Brin was like, you know that thing we learned in math class? I think we can organize our search engine using that, right? They looked at knowledge as something that they can dip from anywhere and put it towards the same thing. And look at what Google's in everything now, right? It's the same principle. Like, let's figure out stuff over here. Let's learn about AI. Let's do self-driving cars. Let's do search engines. Let's do this. Let's do that. Because they're all trying to create this big interconnected thing, right? It's the same principle as the fundamental theorem of calculus. So it's a very important theorem, not only for us, but as like a general life principle. Don't disregard anything. Everything is connected somehow. That being said, now next time I'm going to give you some properties of integrals. That's going to be important and why I put under in quotations. But for now, let's actually do some computational examples. Or at least start some. Don't complete, try to complete it for next time. Don't slack off. Finals is just around the corner. Don't wait on me to do everything. Try to actually forge ahead and do things yourself. Figure out what you know, what you don't know. Fundamental theorem of calculus also marks the last proof I'm going to do for you guys. That's the last thing to do. Like from now on, we're just going to do calculations and I'm going to tell you properties. It's fitting that that is the end of the line. going to do all these because just like with derivatives, you have to do a bunch of problems to actually get used to it. Way more than this, but I'll do a bunch of examples in class. Second example. Find the derivative of the following. I would do something different this time. Like, surprise, here's the test. So let's try to do some of these. Of course, we're going to do these the short way. In fact, the first one, you might notice that we already actually did that. One way you can interpret this expression is, what is the area under x squared on the interval 0 to 1? Right? This is the integral from 0 to 1 of x squared. That's how we would interpret it, the area under x squared from 0 to 1. Let's do 1a. So I'm also going to introduce a notation here. So what you would do, we kind of know what this is. It's going to be the antiderivative of that evaluated at 1 minus the antiderivative evaluated at 0. Here's how you actually write it out. So we would first take the antiderivative. What is that? X cubed over 3. And here's how you actually express that you're doing a definite integral. You don't put a plus c because it's not going to matter. You put a vertical line and you write the numbers on the side like that. So this is here, it's general notation. So if you want the integral of a b of f of x dx, the intermediate step, you write f of x, big F of x, between a and b. And what that cues you to do is take the top number, plug it in. Take the bottom number, plug it in. So we know the equation is this, but an intermediate step, when we're writing it out, right? So we don't write a plus c because there are numbers here. It's a definite integral, not an indefinite integral. You instead write this notation. And so what I'm going to do is I'm going to take the 1, plug it in, minus take the 0, plug it in. Now in general, you do want parentheses around these because the negative sign here would have to distribute, but here there's only one term, so it's actually fine. And the answer here is a third, which is what we got last time with a lot more work, right? We didn't have to find the limit of an infinite Riemann sum. We just found the antiderivative, plugging these two numbers. So that was cool, that was good. That was nice. And the reason why you don't need it is because, just explain that here. Even if you took x cubed over 3 plus c and you left that as the answer, what's going to happen is you have 1 cubed over 3 plus c minus 0 cubed over 3 plus c, and the c's would end up canceling anyway. So you don't write and don't waste your time. You just write the variable part of the antiderivative, and you put that. So you don't need the plus c for definition. Equivalently, B, same guy. So we'd find the antiderivative here. X cubed over 3 minus 1 and 1. I would plug in 1 minus 1. That's of course going to give me a minus 1. Minus a minus 1 gives me a plus 1. This gives me 2/3, which should make sense to you because it's finding this area, which the x squared graph is symmetric about the vertical axis. So that makes sense. In fact, this is something that's true in general. If your f is even, and remember what even actually means, right? This means that f of minus x is equal to f of x. That means it's symmetric about the y-axis. Then, if you take an integral from minus a to a of f of x, it's always going to be in the case that f is even. Not always. If f is even, then integrating from a minus a number to a positive number will always be double the answer you got from going from 0 to the number. So I just take half of it. So if this is my minus a to a, I can just find half of the answer and then double it to get the other half. For even functions, this is going to work out. So you can actually cut down your work a little bit by plugging in 0 for one of the values. Antiderivative of cosine, sine of x, sine of pi over 2, sine of pi over 2, 1, sine of 0, 0. So that one is just 1. In other words, if you wanted to find the sine and you're integrating between 0 and pi over 2, that area is 1. Adds up to 1 square unit. That's cosine. So 0 to pi over 2, the area here is 1. Antiderivative of sine. Negative cosine. That's minus cosine of 2 pi minus cosine of 0. Cosine of 2 pi is 1, so that's minus 1. Cosine of 0 is also 1, so that's negative and negative 1, that's plus 1, and you get 0. And does that make sense? Well, it turns out it does, and this is something that I'll talk a little bit more about next time. If you look at the sine function, notice that it dips below at some point. And I want the area here. Now, based on how we're constructing Riemann sums, because that's what this means, on this side I would have a bunch of rectangles where the height of the rectangle is given by some positive number. However, once I'm over here, now I have rectangles going this way. And you'll notice that the height of those guys will be negative. So it turns out when you actually have a Riemann sum on a function that is below the x-axis, it will actually return a negative area. So the area here is going to be the negative version of the area there. Right? And so this is what it means to be the area under sine x. By area under, we mean the net area. Between sine x and x-axis. But that idea is true in general. You find the net area. So the integral will give you a positive area when your graph is above. It'll give you a negative area when the graph is below. So if you integrate over a region that has both positives and negatives, the negatives will subtract from the positive area. So you're not getting the actual area bounded by the curve, you're getting a net area. But we always just call it the area under the curve, because that's what we were thinking about when we developed it. But that's not exactly correct. So it's the net area. We'll stop there, try all the other examples, and also start practicing what area it's actually asking you to find, especially if it's something that you can graph very easily. Try to figure out what is the actual area I'm looking at here. What does this mean? And we'll stop there. We'll continue the saga on Monday. And I'll talk about some applications of it.